So we saw this conjecture we made, right, from the observation of the first few primes, that what happens to this when I take p minus 1 factorial modulo p, right?
Yes, yes.
So you saw for first three primes, and we guessed that that p minus 1 factorial is nothing but p minus 1 in modulo p, right?
Right.
Right. So yes, so let us try to prove it how it is working. So that is the part B of the same question. So that is to prove it. Okay, so since p is prime, I know that so for every value of a that lies between 1 and p minus 1, so we can find a solution to the congruence x congruent to 1 mod p. So is this true? Can we do that?
For every value between so we need to find x in terms of p or something like that.
No, x need not be no. X need not be in terms of p. X can be other things, because p is just a fixed prime. So p is not a variable. P is a fixed prime,
Right.
and here x is your unknown variable. You have to find x. The thing is, what they are saying is for every a that is between 1 and p minus 1, we can always find a solution to this congruence. So yes, so this is true because p is prime. So a and p is always GCD is 1, right? So GCD of a and p is always 1. So then by the Euclidean algorithm, we can always find. So then we can apply Euclidean algorithm, right?
Right.
So then by Euclidean algorithm, so there exist x and y that belongs to integers, such that ax plus py equals to 1, right?
That x is different than the ax.
Yes, yes, eventually the x will be same. For now, let us take it is some x and y. Okay, let us use some other variables. So maybe p is there, then c and d, suppose. So there exists c and d such that ac plus pd equals to 1, right? So now if I take mod p to this whole equation, then I have ac is congruent to 1 mod p, right? Because pd will become 0.
Right.
So x equals to c is a solution, right? So the above statement is true, right? We can always find a solution to this congruence, right?
Okay.
Right. So the next question is, so after this, that can x be also equal to a mod p? So suppose so what it is saying is when can I have x is congruent to a mod p? So that is only true if I put x equals to a, then a square is congruent to 1 mod p, right?
So repeat that part.
Yes. So the thing is, what are you saying is, so up to this part is clear that these congruence always have a solution, right?
Yes.
So the next question is when the solution will be exactly equal to a.
Oh, you're just like multiplying.
Yes.
So
When the solution will
ax.
be
So you're saying ax equal to 1 equivalent to 1.
Yes, yes.
So below is just, instead of 1, you have a. That's why you have x needs to
Right,
be a squared.
right. Okay.
Mhm.
So when will that happen? That will happen that a square, if a square is 1 mod p, right?
A squared, sorry.
Yes, yes. So what I'm saying is x equals to a will be a solution if and only if a square is congruent to 1 mod p, right?
Right.
Because I'm just putting
Because
x equals to
you,
a.
you you can divide on both sides by a, right?
No, how will you divide?
I mean, if you have like on that, if you have x equivalent to a, and then let's say that x equal to a squared.
Mm, okay. But x equals to a square we are not having, right? We are just taking x equals to a,
Mm-hmm.
right? So
Okay.
x equals to a is a solution. If and only if I substitute x equals to a here, this should hold true, right?
Mm-hmm.
So that is if I put x equals to a, I have this congruence, right? So x congruent to a mod p. So let me name this one. So suppose this is equation 1. So x equals to a is a solution to 1 if and only if a square is congruent to 1 mod p. That is what I'm saying. So if and only if I put x equals to a there, that should satisfy, right?
Why?
Fine.
I mean, why that would be the case?
No, no. I'm just saying one condition. I'm saying that x equals to a is a solution to this congruence. If and only if so x is a solution means it should satisfy this congruence, right?
You're saying x is equivalent to a mod b
Hmm.
if solution, if equation 1 holds.
Yes.
Okay, but I don't see the relation. Like, why?
No, no. I'm saying that this equation have a solution that we understood. Now I
Mm-hmm.
want to see at what condition x equals to a is a solution.
Solution of the first equation.
Yes, yes, of this equation.
Okay.
So x equals to a will be a solution if it satisfies this equation, right? If I put x equals to a, then I get a square equals to 1. That is simple thing I've written down.
If you put x equal to a,
Right.
then you would have a square equivalent to 1.
Mod p, right?
Uh-huh.
Right. So now let us try to understand when it is possible. When is a square, for which values of a, this a square equals to 1 mod p. So now, so a square is congruent to 1 mod p. So this is holds if and only if p divides a square minus 1. Right.
Mm-hmm.
So p divides, I can factorize it as a minus 1 and a plus 1. Right.
Mm-hmm. Mm-hmm.
So now since p is a prime, we have that p divides a minus 1 or p divides a plus 1. Okay.
Yeah.
So and then what is the possible thing is, so since a lies between 1 and p minus 1, so only possible thing is uh, it is either a equals to 1, then first case it will be 0, and or a equals to p minus 1. So these are the only two cases.
A equal to 1, So you're saying P divides A minus 1 and
Right.
P divides A plus 1. So the two cases would be A equal 1.
Yes, yes. The first one, the only solution is a equals to 1, right? Because a lies between that range, right? 1 to p minus 1. So a lies between 1 and p minus 1, right? For any other value of a, p cannot divide a minus 1, right?
Okay.
So from here I am getting a equals to 1, and from here I am getting a equals to p minus 1.
How come A plus 1 becomes P minus 1?
No, no. I am the value of a. A is p minus 1. Then a plus 1 is p. So p divides p. So then it satisfies.
So on the left, you say A minus 1 becomes A equal 1, right?
Right. So if p divides a minus 1, so then I am trying to find out what are the values of a that is true in this range 1 to p minus 1. So the only solution is a minus a equals to 1.
So you're saying P divides 0?
Yes, p divides 0. That is true, right?
Any number divides 0, right?
Yes, yes.
And then the other, you're saying A plus 1.
Yes. A equals to p minus 1. So a plus 1 will be p. And p divides p. So that is true.
Wait. So A would be P minus 1.
Right.
And then P minus 1 plus 1 will be just P, and P divides P. That's what you're saying?
Yes, yes.
Okay.
Okay.
Mm-hmm.
So these are the only two cases, that is a equals to 1 and a equals to p minus 1, where I have this thing is holding true. That is, what I have is a square congruent to 1 mod p. So this is true for a equals to 1 and a equals to p minus 1. So this is what I got, right?
A square equivalent to 1 is true when A is equal to 1 and A is equal to P minus 1. Okay.
Right.
Mm-hmm.
So for all other numbers, that is okay. So the initially what we are trying to find out, trying to find out ax is congruent to 1 mod p, right? So for all other numbers, that is lying between 2 and p minus 2. So 1 and p minus 1 is gone. So I can always find this x that lies between 2 and p minus 2, right? So if I want to find a solution to this congruence in this range, now a lies between 2 and p minus 2, because these two things are gone, right?
Why? I mean,
Yes,
why
tell
they
me.
are gone? I
No, no,
mean, why
this
they are wrong?
this already we found a solution for this one. So when a equals to 1, then x is also 1, because a square equals to 1 has only these two solutions, right?
Okay, if A equals to 1,
Then x is also equal to 1. Then you get 1 mod p, right?
okay, X is also 1, but when A is equal to P minus 1,
Yes, then x is also p minus 1, because if you square a p minus 1 whole square, then you get 1 mod p again.
mm-hmm.
So for these two things, the value of x is again a itself. So that's why we separated this case, these two
Okay.
cases, right? So now we are looking into this range. Now between 2 and p minus 2, right?
Mm-hmm.
So between 2 and p minus 2, there is no more such things, for where x equals to x will be again equal to a. So for each number a, I will find another distinct number between this range such that ax equals to 1.
Mm-hmm.
Right. So let me write it down. For a belongs to uh, this, the numbers can be paired of in such a way that the product is always 1. Product of each pair is 1 mod p, right?
The pair of which ones? A and P?
So yes, so between this one, so suppose a equals to 2, right? We want to find solution when a equals to 2. So when a equals to 2, I will find one solution x that also lies between 2 and p minus 2.
Okay.
Okay, we can pair those two things up, right? Okay, I think this is getting abstract. Let us see an example. I think that will be clear. So let us see an example for p equals to 7, how it is working. Then it will be clear. So the thing is, we are looking at ax is congruent to 1 mod 7, right? And a lies between 1 and 6, right? So for a equals to 1, I know that x equals to 1, right? Because 1 square is 1. Similarly, if a equals to 6, then x is also 6, right? Because 36 is 1 mod 5.
36 is yes 1
Right.
also.
So now let us see what happens to the other numbers. So between 2 and 5. So if a equals to 2, then can you find a solution? So I want to find now 2x is congruent to 1 mod 7. So what is the value of x?
Okay, the value of x. Let's see. 4.
Yes. So for 2 is 8. So that is x. And if a is 3, then so it becomes now 3x.
5.
Right. X equals to 5, right? So what does it give? Now if I take a equals to 4 again I can use that x equals to a, right? X equals to 2, because I can interchange, right? Because 4 times 2 and 2 times 4 is the same.
Right.
Similarly, if a equals to 5, then x is equals to 3, right? So what we can do is, for each of the quantity that is between 2 and 5, I can pair them up. So 2 and 4 I can pair them together, and 3 and 5 I can pair them together, right? Such that their product is always 1 mod 7. This is what I got, right?
Okay, yes.
Yes. And but the thing is, what we have already separated is 1 and 6. So 1 and 6 does not pair with anybody else. 1 and 6 pair with themselves. So 1 comma 1 is a solution, and 6 comma 6 is a solution, right? Right. So now when I want to find 6 factorial modulo 7, that is what I want to find out, right?
Okay.
So when I try to find out 6 factorial modulo 7, so I write down all the quantities. So it is 1 times 2 times 3, 6, right? So I keep 1 and 6 alone. So 1 and 6 is alone, and I pair them, and I pair up with the numbers that we got here. So 2 and 4 I pair up, and 3 and 5 I pair up, right? So now by the what you observed, now if I take modulo 7, then this becomes 1 and this becomes also 1, right? So it becomes 1 times 1 times 1 and 6 mod 7, right? So that is 6 mod 7. So that is what we wanted to prove, right? P minus 1 is congruent to P minus 1 mod P. P minus 1 factorial
is equal to P minus 1 mod P. Okay. Yeah.
So that is what you got. So that is how the proof is working. So except the boundary conditions, that is this is 1, and if you now see in the general case, so this is 1 and this is p minus 1. So other than that, between them, that is between this 2 and p minus 2, all the numbers can be paired up like this, such that their product is 1 in mod p.
Mhm.
So that is what our this congruence gives us.
Right.
So yes. So now I think the proof is clear, right? How we are doing it?
Yeah, I got this example,
Yes. So if
but
we now go back to the general proof,
mhm.
yes. Now here we are separating 1 and p minus 1. Now if I look
Okay.
between 2 and p minus 2,
Mhm.
each number, the numbers can be paired in such a way such that the product of each pair is 1 mod p.
So there are going to be always even numbers to pair.
Yes, yes, even numbers, because p is prime, right? P is odd prime, right? So p minus 1 is always even, right?
Mhm.
So if p minus 1 is even, then again we are deleting two numbers. 1 and p minus 1 we are deleting. So what is left between 2 and p minus 2, that is also even.
Right. So when you say the numbers can be paired off in such a way that the product of each pair is 1 mod p, that is part of the theorem,
No, this is part of the proof, right?
part of the proof. Okay.
Fine.
Mhm.
So after this, then the only one line is left. So p minus 1 factorial, it is 1 times 2 times 3 up to p minus 2 times p minus 1, right? So
Mhm.
this, between this range, I can always pair up, right? Such that when I take modulo p, then it becomes just 1. So only
Yeah,
the,
all of them are going to be one.
right. So this is modulo p. So now we are left with just p minus 1 mod.
Right.
So this is the only observation we have, that so between this range between 2 and p minus 2, I can always pair up the things such that their product is 1.
Mhm.
So
Yeah.
this gives us the result.
Okay.
Okay.
Mhm.
Okay. So the next one is, so compute the value of a minus 1 factorial mod n for some small values of m that are not prime. So yes, we are now trying to find out for other than prime what is happening. Okay, so suppose m equals to 4, then I have 3 factorial modulo 4. How much is that?
3 mod 4, 2.
2, right? Now suppose m equals to 6, so then it will be 5 factorial, right?
5 factor 5 mod 6.
So this is 120, and 120 is equal to 0, right? Because it divisible by 6,
Yeah, 0.
right? So now if m equals to 8, then I have 7 factorial. So I think that is 5040. So that is also divisible by 8, right?
Right.
Okay.
Mm-hmm.
So let us see one more, then we'll get an idea. So suppose it is 9. Then 8 factorial is, I think it is. Okay, anyway, I have to only compute modulo 9, right? So within 8 factorial, so I have 3 and I have 6, right?
Sorry?
Right? So within 8 factorial, it is multiplication from 1 to 8, right? 1, 2 up to 8, right?
Right.
So I have a 3 and I have a 6 also, right? So I can factor out a value of 9. So it is also 0 mod 9.
Mm-hmm.
Right?
Yeah.
Right. So yes. So what is an idea? The idea is whenever m is greater than equals to 6, we are getting that m minus 1 factorial is 0 mod 6, right? Only for 4 it is not true. So we guess that if m is composite and m is greater than equals to 6, then m minus 1 factorial is 0 mod m. Okay.
Okay.
So the thing is, so this is fine, right?
You're saying if n minus 1 factorial. Mm-hmm. Yeah, that's what it looks like.
Right. So also one more observation, if we go back to the previous case. So p minus 1, so that also we can write it as minus 1 mod p, right? Because you can simplify it further, right? Because p minus 1 is minus 1, right?
Right. Mm-hmm.
Right. So we can have a generalized statement after this one. So whenever I have n minus 1 factorial, so these are only these are the only possible cases. So this is minus 1 modulo n if n is prime, right? Then it is if it is 4, 2 modulo n if n is 4, and it is 0 mod n if n is greater than equals to 6 and n is composite. So this is the complete characterization of n minus 1 factorial mod n. So these are the only 3
When
possible cases.
the first one, when you say minus 1,
Yes.
where is that?
No, this is the prime case, right? So that is what I told just now. When p is prime, I get minus 1 mod p, right? P
Okay,
minus 1
that's
factorial.
from before. Okay.
Yes, yes.
You can put also p minus 1, n minus 1 there.
Yes,
It's
yes.
the
But
same.
just to keep it integers, all of them, so I just give minus 1. Okay.
So if n is prime, then minus 1. If n is equal to 4, and 2 is equal to 6, 0. Okay.
Right. So this is the complete characterization, right?
Mm-hmm.
So now we have to prove that. So this part we guessed. So this part we have to prove. So any idea how to prove it? So if m is composite and m is greater than equals to 6, then we have to prove that m minus 1 factorial is always 0 mod m.
We need to prove that a minus 1 is equivalent to 0.
Right.
Composite, you mean not prime, right?
Yes, not prime. So this we have to prove. So actually this is not very difficult. It's easy actually. So since M is not a prime, M is composite, so I can write it as a product of primes, right? I have a prime factorization, right?
Right.
Okay. So since so M equals to P1, P2 up to PR, right?
Mm-hmm.
So now the thing is, since these are different primes, so each of this prime must occur before M, right? Because each of the quantities Pi, this is strictly less than M, right?
Because of mode n, yes, less than n.
Right. Each of the prime factors is less than n. But this M minus 1 factorial, so this is nothing but the product 1 to up to M minus 1, right? So all these
Mm-hmm.
quantities P1, P2, PR lies in the product.
Right.
So each Pi appears in the product,
Mm-hmm.
right? So this product. So when I take modulo, it becomes, that's why it becomes 0. So this implies each of P1, P2 up to PR divides A minus 1 factorial, right?
Each of them divides a minus 1 factorial.
So let us see an example again so that will be clear. So what we
Mm-hmm.
are doing? So let us see for the case M equal to 8, right? So if M equals to 8, then I have M minus 1 factorial is 7 factorial, right? So it is 1 times, okay, let me write down, it will be easier, right? So now
Mm-hmm.
M is 2 times 2 times 2, right?
Right.
So here you can check that 2 is there. 2 also divides this one, 2 also divides this one,
Right.
right? So 2 times this product divides M minus 1 factorial, right?
So you're saying any of those two, which could be other numbers,
Yes, they
they
always
could,
appear before M, right? Because they are smaller than M. So that will come as a term in M minus 1 factorial.
yeah, you're saying any of those factors of 8 are
Right,
divisors of n minus 1 factorial.
right.
Okay, but where do you see that? Like, how did you demonstrate
Hmm.
that?
So the thing is, yes. So we are considering the case that M is a product of distinct prime factors, right?
Uh-huh.
So since each of the prime factors are strictly less than n, then it occurs in this product, right? Because we are going up to all values from 1 to m minus 1. So P1 lies here, right, inside the product.
Since n is composite, n is real, it's less than n. Okay, so you're saying all the PR are within the factorial.
Right.
Okay. But you only have that n is just multiplication of factors.
Yes, yes.
But you
M is,
also, you're also saying that any of those factors are less than all the factors multiply, which is n. But but then you're saying any of those factors are between 1 to n minus 1.
right. So that is true, right? Because each of the factor is strictly less than m. That is clear, right?
Yes, yes.
So these are actually integers, right? All of them are integers, and I am taking the product of all integers up to m minus 1.
Right. So
So
there are all the integers out there
yes, all the
up to.
integers are there. So this
Mhm.
each of the element will belong to this product, right?
Yes, they
So that
will
is
be
what I'm
there
saying.
somewhere. Okay, but I mean, you can say that any of the factors would be within 1 to n minus 1, but how would you know that um, you're saying each individual factor
Yes,
divides n minus 1 factorial,
right.
but you have 2 multiply 2 over there, so you're multiplying all the factors.
Yes, yes. No, the
Yeah.
thing is, okay, let me, this example is fine. This example you understood. But here actually what I'm taking is, so all these things are distinct prime factors.
Okay. But if in the case of 8, they were not distinct price.
Yes, yes. The case of 8, that will also work, but that will, we have to consider it separately. So this one is, for example, you can take another example. So suppose, let me think. So suppose m equals to 2 times 3 times 5, right? So that
Mm-hmm.
will be 30, right?
30.
Right. So now if I look at m minus 1 factorial, so this 1, 2, up to all the way up to 29, right?
Mm-hmm.
So this 2, 3, 5, all the distinct terms appear in this product.
All right. They appear
So,
in the from between 1 to 29.
right. So 2 divides m minus 1, 29 factorial. Similarly, 3
Right.
divides 29 factorial, as well as 5 divides 29 factorial, right?
Yeah. Yeah.
So since all of them are distinct, their product will also divide 29 factorial, right? That is the property of prime, right?
Right. Since all of them, right,
So this will
and
also
they
divide
are,
29 factorial, right?
yeah.
So that is what we are using. So each of P1, P2, PR divides this one, so their product will also divide.
Mm-hmm.
But
I
their
see. I
product
see.
is nothing but the original number. So m must also divide the m minus 1 factorial.
Right.
Okay.
Mm-hmm. Yeah.
Okay. So now the case is when there is not distinct, right? Then what will happen, right?
Mm-hmm.
So suppose m equals to, suppose p1 square. I mean, suppose just for an example, I'm taking that it has two p1 square. Suppose p2, p3, and like this, something pr. So at least okay, we can at least one factor is have double appearance, right?
Mm-hmm.
So then what happens is, so since each of the term is less than m, so p1 square is also less than m, right?
Right.
So since p1 square is less than m, so twice of p1 is less than p1 square, that is less than m, right?
Mm-hmm.
So in the list of 1 to up to m minus 1 in this list, p1 appears as well as 2p1 also appears.
Right.
So that's why I will get all the factors. So that's why when m was 8, I chose in the 2, 4 and 6. Those things I chose to cancel out this 8.
Right.
So here p is 2, so 2 cube. So p, 2p and 3p. So these things are have I chose. So p is 2 here.
Mm-hmm.
So all the terms will appear before up to m minus 1. So it is always possible to divide.
Okay. But over there, they're just saying that 2p1
Right.
is within the factorial.
Right, within the all the set. So the factorial is nothing but product of all the numbers in this list, right, up to m minus 1.
Mm-hmm.
So in this p1 also occurs, 2p1 also occurs, because 2p1 is strictly less than m. So that integer has to be in the list.
Yeah, but why do you replace 2p1?
Because I
Why
want
p1
yes,
square is replaced?
yes, p1, because I want to divide, right? I want to show that m divides m minus 1 factorial. So it is sufficient if I get two factors of p1 out of this list, right? So p and 2p1 is sufficient, right?
Mm-hmm. What do you mean by sufficient?
No, the thing is, what is my aim? I want to show that m divides m minus 1 factorial, right?
So we want to show that a factor that gets duplicated
Yes,
also divides n minus 1 factorial, right?
right.
But then you replace p1 square by 2p1, but we wanted to show that p1 square is there.
Yes, yes. P1 square is, I want to say that P1 square divides a minus 1 factorial. So for that, I get two values of two factors of P1. That is also sufficient, right? If I can individually show P1
I
divides,
see.
so that's why I get P1 and 2P1.
Okay, because p1 and 2p1 they give you p1 square.
Right.
Okay, okay.
Okay.
Mm-hmm. Yeah.
So similarly, we can extend for any value of this thing. So if instead of 2, it was any alpha 1, then here also alpha 1 will be there, and alpha 1 of p1 will be less than always m. So there's that many copies of p1 I will get, so that when we total product them up, so p1 to the power alpha 1 will divide m minus 1 factorial.
Mm-hmm. Okay.
Fine.
Mm-hmm.
So the next one is, so the part A. So 7 power 1734250, that is given to be congruent to 1660565. So suppose this is known, that this is true, this is given to you. So
Mm-hmm.
from here, can we conclude that? So this one is composite.
Yes, because the Fermat's
Right. So
should,
yes, so we
according to
can
Fermat,
conclude
should be
because
one.
of the Fermat's Little theorem, right?
Because should be one,
Right.
equivalent to one.
So yes, we can conclude because of Fermat's Little theorem. If it was prime, then this quantity should be one, right?
Mm-hmm.
Right. So the next part is 129 to the power 64026. That is congruent to 15179. Okay. So this is true. Suppose we know. Then can we conclude that this is a composite?
Yes, right. The same thing as before.
Think about it. Is directly we cannot say, right, because in the pharmaceutical theorem, if you remember, one condition was there, right? So if you recall the pharmaceutical theorem, so it was given a to the power p minus 1 is congruent to 1 mod p, right? If a is not congruent to 0 mod p, right? So this one condition was there, right? If p is a prime and a is not congruent to 0 mod p, right?
You're saying that P is saying that A is not divisor of P, right?
Yes, p does not divide.
P is not a divisor of A, or the other way around.
No, no. A is not congruent to 0 mod p is that p does not divide it.
P does not divide A, so P is not a factor of A.
Yes, yes. So that is the statement, right?
Mm-hmm.
So now, so the thing is when it is, so here it is not equal to 1, right?
Right.
Yes. So yes, also we can see that this number does not divide 129, right?
Right.
So this is composite, that is fine. But actually, what is happening is, so if you check this calculation, that the GCD of 129 and so this is actually 43. So this is not 1. They are not coprime.
Mm-hmm. Mm-hmm.
Okay.
Okay.
So here, so the thing is, actually in the Fermat's theorem, A is not divisible by P. So that thing, that will, if A is a smaller quantity or larger quantity, that will equivalent to say that A and P are coprime.
Okay.
So here actually that is not happening. So that is an
Mm-hmm.
extra condition what you are getting. That the GCD between 129 and 64027, that is 43.
So they are not coprimes, right? Okay.
Yes, yes. But still, we can conclude that this is so this thing is composite. So this we can conclude that is not a problem. Just one observation what we have.
So Fermat-Little's theorem says that A and P they must be coprime first.
No, no. Oh, we have only this condition that A is not congruent to 0 mod P. So let us go to the statement once. Yes. So here we have only the condition that A is not congruent to 0 mod P.
That is not the same as saying A and B they must be coprime.
No, no, that is not same. That's
Or
because P divides A.
P
P,
divides A.
so A is congruent to 0 mod P implies P divides it. So not congruent means P does not divide it.
So A and P.
The thing is that will depend upon the coprime thing what I told. That will depend upon what is the range of A. So suppose A is bigger than P, right?
Right.
So let me write down here. So suppose A is larger than P, right? Then P does not divide A. So that will imply that GCD of A and P is 1, right?
Mm-hmm.
So this is clear?
Yep.
Yes, that is the thing. But if A is smaller than P, then we don't have to look into this because then anyway P does not divide A. That is what I'm saying.
Right.
So that's why here it will work. Still, this will work, but the GCD condition is not satisfying. That is what I was trying to say. So here,
Yeah. But when I
this
say A and B, they must be A and P must be coprime for the Fermat's theorem.
yes. Then we are looking
But
for values of A that is larger than P.
also when A is lower than P.
Is if A is lower than P, then it can happen that GCD is not equals to 1, but still it is composite because in the case of Fermat's theorem, still this condition is satisfied because this is sufficient that P does not divide it. So that is automatically true.
Okay, that is when A is greater than P.
Yes, yes.
When it is lower, you're saying they it's not necessarily that the GCD is 1 because they could have another GCD other than 1,
Yes, yes. But still it will
like in
hold.
this case.
Yes, but still we can conclude because this condition is satisfied that P does not divide it. If A is less than P, then it is automatically satisfied that P does not divide it, right?
Mhm. But in this case A is 129
Yes, A is 129. Yes,
and P is 64027
right.
and A mod P is 129.
Yes, that is still 129. Yes, that is not
So
0.
I okay, that is not 0, right? Okay, right. Mm-hmm.
Right. So yes, so the part C they are saying is um, they are given a congruence which is equal to 1. But from here, can we conclude that it is prime? So 52632 is congruent to 1 mod. So no, right? Because the Fermat's theorem does not say anything about the converse, right? So if it is prime, then it will hold. But if this is given, we cannot say that it is prime, right?
So you're saying this is only to find out whether a number is composite or not?
Yes, yes. So the contradiction is for composite, right? But we cannot say it is prime because Fermat's theorem is only one direction. It does not give the opposite direction, right? So this works only in one way.
In which way?
So if it is given that P is prime, then I can say that a to the power P minus 1 is 1 mod P. I cannot conclude that whether it is prime. So that we cannot conclude, right?
You cannot conclude that 52633 is prime.
Yes, that you cannot say, right? Because the Fermat's theorem says that if P is prime, then I can say that a power P minus 1 is 1 mod P.
I see. So only if you start with a P prime, then the Fermat's little theorem works. But if
Yes,
you
yes.
don't know if P is prime, then you cannot say that.
Right. So in fact,
Okay.
this has a factorization that is 7 times 73 times 103. So this is not a prime.
Mhm. I see. Yeah, I see.
Okay.
Mm-hmm.
So today we'll stop here then.
Okay.